Wanted to work through a famous problem of a network of resistors and figuring out the equivalent resistor to the network of resistors. This famous problem involves 12 identical resistors that are connected together to form the 12 sides of a cube. I've pictured the arrangement over here on the top left. So if you look at the cube, it has 12 sides. So there's the front face here that has 4 sides to it. There's a back face here that also has 4 sides to it. And then there's 4 connections between the front face and the back face at the top left and right, bottom left and right corners. So there are 12 sides to this cube, and each of those sides has a resistance of 1 ohm. And the question is, in this cubic arrangement of resistors, what is the equivalent resistance between this corner upstairs here? This is going to be the back top left corner, and this corner down here. This is the front right bottom corner. So they're opposite corners on the cube. What's the equivalent resistance between these 2 terminals, between these 2 points? Now, this looks like a horribly complicated problem. This is a problem that we're going to solve. We're going to solve it using our understanding of resistors in series, our understanding of resistors in parallel, basic rules for combining resistors in series and parallel to make equivalent resistances. But we're going to add to that one additional idea that makes this problem solvable in a fairly simple way. And it's an idea that I'll refer to as symmetry. And we're going to talk about the symmetry involved in this cube. Before we do that, I'm actually going to solve a similar but simpler problem. It's the problem that I depicted down here. It's the problem of the resistance of a equivalent resistance of this arrangement of 4 resistors in a square rather than a cube. So this is just a 2-dimensional square. The more complicated problem is a 3-dimensional cube. In the square, we've got 4 sides for our square, and we're going to imagine that each of those 4 sides has a resistance of 1 ohm. In this case, because it's just 4 sides, I've literally marked each of the resistances 1 ohm. And again, similar type of problem here. We're going to think about opposite corners of our square, like we thought about opposite corners of our cube. What is the resistance between this top left corner and this bottom right corner? What's the resistance there? Again, we're going to solve this problem using our understanding of the equivalent resistance of resistors in series and resistors in parallel. But I'm also going to add the idea again of symmetry in this problem. So we're going to do the square first, and then we're going to do the cube second. By doing the square first, the square is a problem that you could solve using series and parallel resistances without the idea of symmetry. We could just solve it with parallel and resistances alone. It would be a straightforward problem. So one that we readily understand. But I'm going to add into it the idea of symmetry so you can get an idea of how the symmetry works. And then we're going to go to the cube. We're going to solve the cube with our ideas of parallel and series resistors. We're going to add in symmetry like we did in the square. Adding in symmetry in the cube allows us to solve it in a fairly straightforward way. It's really the key in solving the cube. It's not necessary in solving the square. It's interesting in solving the square, but it's essential in solving the cube. It's the only way we're going to solve the cube problem. Okay, looking at the square and starting to solve the square, if I look at the arrangement of resistors in the square, and I know the locations of the two terminals where we want the equivalent resistance, I can see that the circuit has really two arms to it. This one that goes down, then right, and this other arm that goes right, then down. So there's two arms to the circuit, two parallel arms to the circuit, and each of those arms contains two 1 ohm resistors. So there's two 1 ohm resistors on this arm upstairs here. There's two 1 ohm resistors on this arm downstairs here. So the total resistance of this lower arm is actually 2 ohms. The total resistance of this upper arm here, that's also 2 ohms. So it's like we got two 2 ohm resistors in parallel to one another. Well, if we got two 2 ohm resistors in parallel to one another, we can use the rules for parallel resistances, that the equivalent resistance, the inverse of the equivalent resistance, the reciprocal of the equivalent resistance, is the sum of the reciprocals of the individual resistances. So the reciprocals of the 2 ohm resistors are 1/2, a half downstairs here on the left, a half upstairs here on the right. So we've got to add the two halves together, we get 1. That's the reciprocal, the inverse of the equivalent resistance. We want 1 over that, so the reciprocal of 1 is itself 1. So the equivalent resistance for this circuit, I've just figured out in my head, right, is equal to 1 ohm. And that was just based on the rules of equivalent, the rules of series and parallel arrangements of resistors. I'm going to solve this problem now, adding in the idea of symmetry. Adding in an idea of symmetry as applied to the currents that are flowing in the circuit and the electrical potentials that appear in the circuit. So when I connect the two terminals to a battery, there's current that flows in, say, from the top right, left, and flows out on the bottom right. There's potentials between the top left and the bottom right, and those potentials get shared out across these resistors. The current is shared out across these resistors. What symmetry does the sharing of the current, the sharing of the potential have? Well, the key thing that I want to point out is that if we go to the two other corners, there's a corner down here and there's a corner up here. The current that flows down to the bottom left corner and the current that flows to the top right corner, those are equal currents. There's equal sharing of the current coming in at the top left terminal to go through these two paths, to go through these two locations that I marked in green. That's because the arrangement has a symmetry. It's a square built out of 1 ohm resistors. Every resistor is a 1 ohm resistor. If every resistor was a different resistor, it wouldn't have that symmetry, and the currents flowing out of this node here horizontally towards the right or vertically downwards would not be equal, but because of the symmetry, they are equal to one another. So there's equal currents going down, there's equal currents going right. Also, something that's equal is the potential of these two locations. This one on the bottom left, this one on the top right. They're equal potentials. They're equal potentials because there's equal currents that flow down the two arms that lead to them. So there's equal potential drops across the two resistors on those two arms. So these are equal potentials. If 2 points are on equal potentials, what that means is that you could connect them with a wire, and I've just done that here, and not change the circuit. And by not changing the circuit, I mean not changing the path that the currents flow, not changing the potentials in the circuit, not changing the equivalent resistance in the circuit. Why does this wire not change the circuit in any of those ways? The current, the voltage, the equivalent resistance. Well, this end of the wire, bottom left, this end of the wire, top right, they're at the same potentials. If they're at the same potentials, no current flows through this wire. And so since no current flows through this wire, then it has not changed the circuit whatsoever. There's still the same currents down the wire on the left here. There's still the same current down the wire upstairs here. And there's still the same currents on the wire on the right and downstairs here. There's the same potentials everywhere, and the equivalent resistance is unchanged. So that's a symmetry idea that I've used to redraw this circuit in an equivalent way. Now, if I was to use that idea, I could solve the resistance, the equivalent resistance of this arrangement with this new circuit where I've added this one wire. If I was to do that, let me draw the layout of this circuit in a revised fashion with this additional wire in here. So here's the equivalent circuit to the square, the 4 resistor square with the 2 terminals where I've added this extra wire. So if you look at this circuit now, where I've redrawn it here, here's the terminal, that's the top left. The current flows in through that terminal. It's split to these 2 resistors, the one on the left-hand side, the one upstairs here. We said that we can add a wire that connects the ends of these 2 resistors upstairs here and on the left here. Notice it also connects the ends of the other 2 resistors on the right and on the bottom here. So adding that wire, I can draw it like this. Look, these 2 ends of the resistors that we flow through on the way into the circuit are now connected by wires. Also, the 2 ends of the 2 other resistors that we're going to flow out of the square through, they're also connected together by wires. And then finally, as we flow through the bottom 1 ohm resistor, the right 1 ohm resistor, we flow towards the output terminal here. And so these are connected on this end. And so this is an equivalent circuit for this circuit here, the square with the extra wire that we added based on symmetry. If we look at this circuit here, on the left, we got 2 1 ohm resistors in parallel to one another. So this would be half an ohm. Again, I would get that by the rule of parallel resistors, that the reciprocal of the equivalent resistance is the sum of the reciprocals of the individual resistances. So I'd be adding for the individual resistances 1/1 plus 1/1, which would give me 2, and the equivalent resistance is the inverse of that, so it's half an ohm. And the same thing over here. These are 2 1 ohm resistors in parallel. That would be half an ohm. And so the total resistance here of the whole thing would be the sum of these 2 half ohms, because they're in series. That would give me 1 ohm. And that would be a second way of solving this problem. Now, in the case of the square, the second way really didn't make solving the problem any quicker. The second way, well, it's kind of interesting that you can put a wire here and make no difference, and you can redraw the circuit involving different arrangement of parallel series resistors, but it didn't make solving the problem any quicker. That's not true for the cube. This idea of symmetry of the currents, symmetry of the potentials, makes solving the cube a reasonable problem. Without the idea of symmetry, solving the cube would be an extremely, incredibly complicated problem. So now let's move to the cube. So I'm moving to the cube, and the first thing I'm going to do now is apply the idea of symmetry. Remember, the idea of symmetry works here like it worked on the square, because the arrangement of resistors is an arrangement of identical resistors. this argument wouldn't work if the resistors were different resistors. The other point is that this idea of symmetry is an idea of symmetry about the currents that flow in the arms of the circuit, about the potentials that appear in the arms of the circuit. So we can see for this particular arrangement that there will be certain wires that we know by symmetry have the same currents, certain locations, corners, nodes, that by symmetry will have the same potentials. When we figure out what locations have the same potential, we can perform this trick of adding an extra wire connecting locations that have the same potential. This changes the circuit arrangement, but it doesn't change the action of the circuit. It doesn't change the performance in terms of the currents and the voltages and the equivalent resistance. So we're going to apply symmetry, and we're going to add some extra wires, and we're going to see what we get. And this is really, I can't stress enough, this is a fantastic example, this cube, of how this works, of how useful this idea is. So let's start with the top corner over here. So it's at the back of the cube. It's at the top and it's on the left. So we're coming in on this wire here. And the current that comes in there gets split into three. So some of it goes down this edge at the back here. Some of it goes towards the right, horizontally, on this edge at the back here. And then some of it's going to flow forward on this this piece that's kind of emerging from the whiteboard. So we've split our current into three. Now, that split into three, because the resistors are all the same, 1/3 goes down, 1/3 goes right, and 1/3 comes out of the whiteboard. That also means, since the 1/3 that goes down, the 1/3 that comes out of the whiteboard, and the 1/3 that goes right are going through the same 1 ohm resistors, that the potential at this location here, the potential at this location here, the potential at this location here, where those three currents are going to, are actually all the same. And we could, if we chose, connect all those points with wires. And so that's what we're going to do. Before we do that, I want to walk down to this other terminal downstairs here and talk about that terminal. So the current that flows through the cube ultimately is collected and exits through this terminal down here. This terminal down here gets current that's coming in through this bottom wire here. It gets current coming in through this wire on the right and at the front here. And it also gets current from this wire here. So it gets current flowing in from these three paths. Now, again, because of the symmetry, these three currents are the same. They're 1/3, 1/3, 1/3 of the total current, because this is a symmetric arrangement of 1 ohm resistors. That means that the potentials at the opposite end of the wires that those currents were flowing along, so that's this end of the wire here, it's at the front, it's on the left. This end of the wire here, it's at the front, it's upstairs. And this end of the wire here, it's kind of at the back. This is the wire that comes out of the whiteboard. Those potentials are all the same. So we could also connect these three red points with wires and not disturb the circuit. And again, that's what we're going to do. So let's stand back and we're going to redraw this circuit. And I think what I'm going to do is I'm going to redraw the circuit over here on the right-hand side. And then I'm going to explain exactly how it matches this arrangement here. And this redrawing is the key to solving the problem. Once we redraw the circuit with these extra wires that we've noted that we could insert because of the symmetry of the cube, you'll see that this is an easy problem to solve, a straightforward problem to solve. Okay, here's my equivalent circuit for the cube with these extra wires added. How did I arrive at this? How did I figure this? Well, let me start explaining it. Firstly, if you count up how many resistors I've got in this arrangement here, I got 3 on the left, I got 3 on the right, I got 6 in the middle. That's 12 in total, 3 plus 3 plus 6. That is the right number of resistors in the cube. So firstly, there are 12 resistors here. There were 12 resistors over here. Coming in on the top back left. So coming in here, I come in and my current is split into 3 and passes through 3 resistors. And we agreed that that was the situation here. Our current, as we come in, it goes down at the back, it goes right at the back, and it comes out of the screen here. It heads towards these 3 points in green, and we said we could connect those together by wires. And here they are. They're connected together by wires. So this is the sort of extra symmetry-based bit of the circuit that I added that doesn't disturb the currents and the voltages in the circuit. So this piece here is the current flowing to the 3 green points that we identified we could connect together. So I hope we're okay there. Similar problem, similar situation over here on the right-hand side. This is the current that's flowing out of the circuit. And the current that's flowing out of the circuit came from 3 arms, if you remember. This front bottom arm, this front right arm, and this other arm that's coming out of the whiteboard. So these 3 resistors are these 3 arms, and we said again by symmetry, these 3 red points are at the same potential. We can add a wire, connect them together without disturbing the circuit. So that's what this piece is here. That leaves these 6 resistors that I put in parallel. So all of these 6 resistors connect a green point to a red point. They all connect a green point to a red point. So they're all, in that sense, parallel with one another. And they are the remaining 6 resistors. Let me mark them just to prove that they're, every one of these 6 resistors is between a green point and a red point. The red point, I'm going to mark it here. And the green point, I'm going to mark it here. And they correspond to the red and green on our cube over here. And I'm going to just show you where, and I'm just going to mark where these 6 resistors are. And so that's what I've done on the sketch here. The black lines, the black sides are now the locations of the resistors that connect all the green points to all the red points. Remember, the green points are all at the same potential. The red points are all at the same potential. And so if we are connecting a green point to a red point, we're connecting between the same potentials. And so those resistors will be in parallel with one another. They are between connected wires at the green point and the red point in our circuit where we identified the symmetry. So here are the 6 resistors or the 6 wires. I've indicated them in black. If you look, there's 2 on the front face. So this vertical wire here on the left, this vertical wire upstairs here. There's 2 on the back face. There's this one at the back, which is vertical. There's this one on the back that is horizontal. And then there's this wire that's coming out of the screen and this wire that's coming out of the screen on the bottom left and on the top right. All of those 6 wires or 6 resistors are the ones that are connecting a green point to a red point. So it's green point here, red point here, 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 and so on. They're all connecting the green points and the red points, i.e. whatever potential the green point is, whatever potential the red point is. And so this is the equivalent circuit. Now, this is fantastic because this circuit we can solve. We can solve this one in our head. This is a circuit in which you've got three arrangements in series with one another. This arrangement on the left, this arrangement on the right, this arrangement on the center. The arrangements are parallel arrangements of resistors that are equal. So we got three here. We got three here on the right. We got six here in the middle. If you have three 1 ohm resistors in parallel to one another, the resistance of that is 1/3 of an ohm. You get that by the equivalent inverse of the equivalent resistance being the sum of the inverses of the individual resistors. So you've got sum of 1/1 plus 1/1 plus 1/1. That's 3. And you want the inverse of that to get the equivalent resistance. That's 1/3 ohm. So this is 1/3 ohm. This other resistance over here on the right-hand side, that's also, this is 1/3 ohm too. It's three resistors in parallel with one another. This one in the center, same argument, right? And this is 6 resistors in parallel. So it'd be 1/1 plus 1/1 plus 1/1 plus another 1/1 plus another 1/1 plus another 1/1, which is 6. And the inverse of that is 1/6. This is 1/6 of an ohm, the one at the very top. So let's add that in. And then these three resistors, 1/3 ohm, 1/6 ohm, 1/3 ohm, they're in parallel with one another. Sorry, they're in series with one another. So we just got to add 1/3 plus 1/3 plus 1/6. 1/3 is 2/6. And so we got 2/6 plus 1/6 plus 2/6. So this is going to be 5/6 ohms. And 5/6 ohms is the equivalent resistance of this circuit. Well, I hope you enjoyed that. I mean, I thoroughly enjoyed that. That problem of the cube to me is just pure fun. We applied our rules about resistors in series and parallel. We were thinking about circuits that involved a collection of equal resistors to keep things simple and straightforward. What that brought into the problem in this arrangement of equal resistors arranged in a square or equal resistors arranged in a cube is the possibility of adding to the rules of resistors in parallel, resistors in series, symmetry arguments. Specifically, symmetry arguments, kind of pattern arguments, we applied to the currents that are flowing in the circuit, and we applied to the potentials that appear in the circuit. We were able to spot arms of the circuit where the currents were the same. We were able to spot locations in the circuits where the currents were the same. Then we used this clever trick, this very clever trick that simplifies the circuit by adding actually more wires to the circuit. We added extra wires to the circuit to simplify the circuit. We added extra wires connecting locations at the same potential. If you connect two locations at the same potential in a circuit, there's no potential hill that will drive a current down that extra wire. There's no current that flows down that extra wire. You actually don't disturb the circuit whatsoever. And so with those extra wires added to the circuit, we redrew the square, figured out the equivalent resistance of the square. We redrew the cube, figured out the equivalent resistance of the cube. It's how we were able to solve the cube. Otherwise, it's a very, very complicated problem. Having figured out the resistance of the cube of 12 identical resistors, having figured out that it's 5/6 ohms if the individual resistors are 1 ohm. You could apply that understanding to figure out, for example, the capacitance of a arrangement of capacitors, which was a cube of 12 identical capacitors. So maybe they were 1 microfarad capacitors arranged on the sides, the 12 sides of a cube. What's the equivalent capacitance of that arrangement? But you could go about that problem exactly the same way. You could use the same arguments about the symmetry or the sharing of the currents between the different arms in the resistor network, and hence the symmetry of the voltages at corners of the resistor cube. You could make those arguments about the sharing of the charge on the plates of the capacitors on the different arms of the circuit, and hence the potentials on the different corners of the capacitor circuit. It would be exactly the same arguments for the capacitor circuit and for the resistor circuit. It's quite wonderful. Based on that, you could write down a equivalent, you could draw an equivalent diagram for the capacitor circuit that uses extra wires that connect locations at the same potential, just like you used extra wires to connect locations at the same potentials in the resistor circuit. You could draw the capacitor circuit. It would be exactly the same circuit, except all the capacitors, all the resistors, the 12 resistors, are now replaced with 12 capacitors. It looked just the same. It's a simple arrangement of 3 parallel capacitors, then 6 parallel capacitors, and then another 3 parallel capacitors, with that 3, 6, and 3 blocks of capacitors in series with one another. So it would look exactly the same as the resistor circuit. Well, what would be the equivalent resistance capacitance of the capacitor circuit? Well, like for the equivalent resistance of the resistor circuit, you would use the rules for capacitors in parallel and series versus the rules for resistors in parallel and series. Now, the rules for capacitors and resistors are kind of the reverse of each other. When you've got capacitors in parallel, you add up the capacitances. When you've got capacitors in series, you add up the reciprocals, inverses of the capacitances. And so the rules are reversed. So for the capacitors, you've got 3 capacitors in parallel with one another. If they're 1 microfarad capacitances, that's a total of 3 microfarads. If you've got 6 capacitors in parallel with one another, if there's 6 identical 1 microfarad capacitors, that's 6 microfarads. So our arrangement of 3 capacitors in parallel, and then 6 capacitors in parallel, and then 3 capacitors in parallel, that is an arrangement of 3 series equivalent capacitances that are 3 microfarads, 6 microfarads, 3 microfarads. What's the capacitance of 3 microfarads, 6 microfarads, and 3 microfarads in parallel with one another? Well, that actually is 6/5 microfarads. You're making a smaller capacitance than any of the individual capacitances when you arrange them in series. That 6/5 microfarads is just the inverse of the result that we got from the resistors, which was 5/6 microfarads. It's just the inverse because all the calculations of the equivalent resistances are the inverse of the resistor cases. And so it's actually quite fantastic that once you've solved the cube of resistors, you can solve the cube of capacitors just by remembering the resistor answer was 5/6 ohms, and recalling that the rules for combining capacitors is opposite to the rules for combining resistors, to tell you that the equivalent capacitance for the capacitor cube is 6/5 ohms. Wrong units, sorry. 6/5 microfarad.